Today you can see our lesson is 5.2, and we've been talking about probability in our previous lesson, and now we're going to continue that thought of calculating probabilities, but today it's going to be in the realm of medical testing, and as you can see, medical testing and conditional probability. So the issue here, just to kind of give you a little bit of background before we dive into the lesson. As we look at medical testing, and they are prevalent in our society, very important, used extensively, but the issue of medical testing is that they're not 100%. They're not infallible. Tests that are supposed to detect the presence of disease, they're not going to do that with 100% accuracy. And then alternatively, to try to rule out the absence of disease, same thing. A medical test is not going to do that at a 100% clip. So what they do, even though they are very important in our society, what they do for us is they give us a probability that well, I'll just go ahead and fill in the blank here. Instead of giving us a certainty that a patient actually has the disease, they give us a probability that a disease is present. And then just to go up and fill in our blanks, we know this in our society, athletes are routinely being tested for banned substances, especially during Olympic season and then periodically in professional sports. Probably at some point in your life, you're going to have drug screening for a particular job. So we'll say drug screening for employment purposes. And then, of course, we've all gone into our doctor when we suspect that maybe we have COVID or flu or strep or any of the other diseases that we could possibly pick up, and there's a really quick test that we can be given. That's very helpful, but again, it just opens up the probability that the disease is present, and it doesn't do it with 100% certainty. So that's kind of laying the groundwork for today's lesson. So we're going to talk about two terms in light of this lesson on medical testing. The first term you'll hear is sensitivity, and then we'll talk about specificity. What is that referring to when it comes to medical testing? Well, first of all, let's talk about four possibilities. The results of medical tests can basically fall into one of four categories. They could give us what is called a true positive. So a person tests positive and they actually do have the disease that's being tested. We could potentially have what is called a false negative. So the test says that the person does not have the disease, but the person actually does. Okay, so according to the test, it's negative, but we would call that a false negative. Then we have the scenario where a person tests positive, but they don't have the disease. So the test says yes, but actually it's a no as far as the disease is concerned, so we call that a false positive. And then a true negative, the person tests negative and they don't have it. So the test is basically doing what it was designed to do. In both of these cases, with the true positive and the true negative, those are ideal. But because that doesn't happen all the time, it opens up the possibility, the probability, that these other two scenarios could actually take place. So let's do some definition work here. Sensitivity, just to get you seeing these words again, spelling them out. Sensitivity and specificity. There are measures of a test's accuracy in the following terms. These these terms of trying to identify true positives, true negatives, false positives. So the sensitivity of a test is the probability that the test will detect the disease in a person who does have the disease. All right, so we're looking for the presence of disease in a person that actually does have it, and the test's ability to accurately detect the disease is called the sensitivity of a test. The specificity of a test is the probability that the test will give a negative result for a person who does not have the disease. So sensitivity, going to our next slide, the sensitivity measures the test's ability to detect correctly the presence of a disease. And then the specificity is it's measuring the test's ability to identify correctly the absence of disease. And we have two mathematical formulas to calculate each of these situations. You can see sensitivity is basically the true positives over all the people who have the disease. That would be the true positives and the false negatives. And then to calculate specificity, probability, we would take the true negatives over all the people who do not have the disease. When we do calculate these measures, they're written in percent form, and we're going to round them to 1 decimal place. And that'll be consistent throughout all the problems that we do in today's assignment. Well, let's do a couple of examples of calculating sensitivity and specificity. So in this first table, we have results of a study, a test for COVID-19. You can see our true positives, false negatives, true negatives, false positives. Use these data to estimate sensitivity and specificity. All right, so to calculate sensitivity, I would take the people that actually tested positive divided by all the people who actually have the disease. So if you notice, this column is labeled as people that have COVID-19. Now the test accurately detected most of those, but not all. Okay, so to find the denominator to get our ratio, our percent, we're going to have to add these together, and that would be 6,296. So getting that in percent form, we would say it's 87.5%. All right, the specificity, looking at the column that shows the people that do not have it, well, the test accurately identified most of the people who don't have it. That's the 6,505. They tested negative and they actually don't have it. We call those true negatives. But we have to account for these 26 that were not accurately identified. So these two numbers added together will become our denominator. So it's the people who actually tested negative over all the people who do not have COVID-19 in this case. And now we go to our calculator to calculate the percent, and that's going to be 99.6%. Okay, another example, same type of process. This is a different test that is given. So let's calculate the sensitivity of this test. The test ability to accurately identify those people who do have the disease. Well, it identified 165 correctly out of a total of 194. So the percentage of identifying the people who accurately did have the disease, when we go to our calculator, that's going to be 85.1%. And then the specificity, measuring the accuracy or the ability of the test to accurately detect those who do not have the disease. Well, it did that for 355 people, but there was a total of 410 people tested. And it missed, in other words, these 55. So when we do the percentage, it accurately spotted the absence of disease about 87% of the time of the people that took the test. All right, those are some examples of looking at table data and calculating sensitivity and specificity. Looking at it a different way, if we're given the sensitivity rate of a particular test and we know how many people took the test, then how many people tested positive? So this is saying that 93% of the people tested positive, in other words. So pretty easy to calculate this. We'll take all the people who took the test and we'll multiply by 93% as a decimal, and 419 people tested positive. Okay. The specificity is going to tell us the test ability to accurately detect the absence of disease. If 300 people who do not have the disease took the test, and 87% is the specificity rate, then how many people will test negative? So we would come up with 261. All right, let's move on to our next topic. We're going to be talking now about positive predictive value, PPV, and then negative predictive value in just a bit. So as my paragraph here is stating, we get this idea that if a person did test positive and there's a high sensitivity and specificity, then we should conclude that the disease is almost certainly present. But we have to consider another factor, and that is the prevalence of the disease. The prevalence of a disease in a given population is the percentage of the population that actually has the disease. And that's what PPV is going to take into account, and NPV, where sensitivity and specificity do not. We're going to factor in this idea of prevalence of the disease in this calculation. So for a population with a known prevalence, the positive predictive value also known as PPV of a test is the probability that a person in the population who tests positive actually has the disease. So it's just saying it another way. If a person tests positive, what's the probability that they actually do have the disease that they tested positive for in a certain population with a given prevalence? And then the flip side of that, for a population with a known prevalence, the negative predictive value or NPV of a test is the probability that a person in a population who tests negative actually does not have the disease. So you can see our calculation is a little bit different. For PPV, we're going to do true positives over all positives. Before, when we did sensitivity, we did true positives over all people who had the disease. So slightly different way we get this calculation, and I'm going to show you on the next slide hopefully something that will help you keep all four of these calculations straight. I think it's a nice way to remember each of them. And then negative predictive value, the true negatives divided by all negatives. Okay, so here's that slide I was telling you about. I actually saw this being presented by a physical therapy instructor, and I thought it was good. I wanted to share it with you. So we have 4 different calculations for the 4 different measurements of testing that we've talked about so far in this lesson. So using the table, you have to understand how this table goes, and this is the test result. Test is positive, test is negative on the left side, and then across the top is really what happened. The person either has it or they don't. So we have here, just like we said at the beginning of the lesson, it's set up with the true positives, true negatives, false positives, false negatives. So if we want to calculate sensitivity, we see this arrow, and I heard this professor use the analogy of a sensitive person. If you're overly sensitive in your personality, you could very easily spiral downward. So in a way to help you remember the direction of this arrow. And the non-arrow, the side that is not arrow-shaped, is the numerator. So the denominator is going to be the 2 values added together. So you can see how that's made. The opposite of the arrow is the numerator, the true positives, and then the arrow takes into account the sum of those 2 values as the denominator. All right, and that's how we calculate sensitivity. Specificity, just trying to come up with a way for you to remember this. We're going on the negative side of the chart, and now the arrow is going up. And I shared with the class, just thinking about prayer. You know, our prayer life is such an important part of our day-to-day walk with the Lord. And prayer needs to be specific. You know, too much of our prayers are general. You know, bless everybody, you know, bless my family, bless the missionaries, instead of specifically naming people in our prayer life and actually getting to know their needs and bringing those needs before the Lord specifically. So to me, that's a way to remember specific prayers go up. And so again, the way the arrow is constructed, the non-arrow part is the numerator, and then these 2 together represent the sum of these 2 values represent the denominator. So we have sensitivity going down, that first column, specificity going up, second column. And then down here we have positive predictive value. Okay, so it's easy to remember these top 2 are positives, and we go in a positive direction. If you think about the number line, the arrow is going to go in the direction that numbers go positive. And again, same thing, the non-arrow side is the numerator, and then these 2 together, added together, represent the denominator. And then the negative predictive value, we're going in a direction across the bottom. Of course, these are both negatives, and we go in a negative direction, just like the number line. Numbers get smaller, they get more negative as we go to the left. So true negatives would be on the top of this fraction because it's not the arrow, and then these 2 together would be the denominator. So hopefully this will help you because we do a lot of calculations in this lesson with these 4 ways of measuring testing, and I thought this would be a good way to try to keep them distinct in your mind and how to come up with the calculations quickly and easily. So let's take a look. We have this example, injection drug use is among the most important risk factors for hepatitis C. 2 studies were done using hepatitis C with a 90% sensitivity and specificity. One test involved a group that was representative of the overall U.S. population, we'll call that general population, which has a chronic hepatitis C prevalence of about 1%. And then the other test was on a population of older and former injection drug users, and the prevalence there, of course, you would imagine is much higher. It's 80%. So the results of are shown in the table below. It's actually 2 tables if you want to think about it, because we had this general population results and then the older population results. So let's calculate the PPV for each of the populations. So just thinking about our previous slide, We go across the top. I'll do the general population first. So we take 9, and then we put that over the sum of 9 and 99, which is 108. And our normal procedure here is to do percent form in one decimal place, so that would be 8.3% for the general population. And then for the older population, same thing, we would do 720 divided by the sum of these, which is 740, and percent form to the nearest tenth would be 97.3%. And now, example 6, using the same table, let's calculate the NPV. Well, now we're going across the negative row and we're going in a negative direction. So for the general population, we would have 891 as the numerator over 892, the sum of those two, and that would be 99.9%. For the older population, we would have 180 divided by the sum of those, which is 260, and that would be 69.2%. Okay, so example of how these work, both negative predictive value and positive predictive value, factoring in prevalence of the disease. All right, here's another example. You'll do a couple of problems like this in your assignment. Crohn's is a relatively rare in the US. The prevalence is about 0.18%. The population of the US is about 330 million. So letter A, how many people in the US, according to these statistics, suffer from Crohn's? So we're going to take the 330 million and we'll multiply by that percentage, which would be 0.0018 as a decimal. And that should be in millions, about 0.59 million. Okay, so that would be our answer for part A, 330, just checking my number here, 0.594, so we'll do 2 decimal places for all of our answers. Okay, so part B is going to require that we fill in this table. There's a screening test for Crohn's. It has a sensitivity of 80%. It's accurately catching people that have the disease at an 80% accuracy, and specificity at 90.2%. So it's accurately detecting the absence of the disease at a 90% accuracy rate. Use this information to complete the following table, which shows the results we would expect if everyone in the US were tested for Crohn's. Okay, so we were already told that there's 330 million people and everybody gets a test. All right, so using our answer for part A, 0.59 million people have Crohn's using this percentage. So I'm going to put this, we're going to put a little total here. We'll say that this is 0.59. Well, induction, or thinking about this logically, if 0.59 million have it, then 300 minus 0.59 million do not. All right, so just doing some subtraction here, and we would get 299.41. Sorry, I said 300 million, but it's actually 330. Sorry about that. So let's try that again. 330 minus 0.59. Okay, 329.41. So these two totals should add up to 330 million. They represent all of the population, those who have Crohn's and then those who do not. Okay, So let's now turn to our sensitivity rating. It says that of these people that have the disease, the test said 80% of them would test positive. So let's see what that number is. 0.59 times 80%, that's 0.472. So the test would say 0.47 million have the disease. So since that's 80% according to the sensitivity rate, then that means 0.12 would test negative, even though they have the disease. 0.12 million would test negative. All right, now let's turn to the specificity rate, 90.2%. So of the 329.41 who do not have the disease, let's multiply that times 90.2%, and that gives us 297.13 according to the test results. The test would say that many would test negative because that's the specificity percentage, which means the difference between these two numbers, the 329 and the 297, would be those who do not have the disease but they tested positive for it, 32.28. And there's our complete table. And then part C is we're going to use this information in our table to calculate the PPV for the general U.S. population. So PPV, we're going across the top. We would say 0.47 divided by the sum of these two numbers, 32.28 plus 0.47, that's 32.75. And as a percent to one decimal place, that would be 1.4%. Okay, so there is our answer for example number 7. And then finally, we'll wrap up our video here, the notes, with conditional probability, the probability that one event occurs given that another event has occurred. So let's look at this table and see if we can figure out a methodology for coming up with conditional probability. So the table below was adapted from a study of a test of for TB among patients diagnosed with extrapulmonary TB. You see our numbers here. Calculate the conditional probability that a person tests positive. Okay, so these two numbers here involve people who test positive, but let's read on. Given that the person has TB. Okay, so we've narrowed it down. The person tests positive would be our numerator. Okay, so it's kind of like this. It's setting up a fraction for us in the way that this is worded. A person tests positive, all right, and the given will help us construct the denominator. So 446 will be the numerator, people that test positive, but it's not the 15 because it has to be given that the person has TB. All right, so all the people that have TB are these two numbers added together, which is 662. All right, so we put that together and go to our calculator, and that gives us 67.4%. All right, let me erase this, and then we'll do another example. The probability that a person tests negative, all right, so now we're down on this bottom row, given, all right, given that the person does not have TB. Okay, so now we're going to let 323 be our numerator, test negative, given that the person does not have TB. And so the denominator is going to be those two numbers, all the people that do not have TB, which would be 338. So in percent form, that would be 95.6%. Okay, I think we have concluded the notes. I think you are now ready to do some practicing with the assignment. And if you do have any questions about this, feel free to reach out to me. And Otherwise, I will see you next time.